Great, welcome back. Okay, so we're going to continue now talking about ways of moving heat around in the atmosphere. And so far we've seen conduction, and we've seen the processes of convection and advection. Finally, we're going to talk today about radiation, and radiation is going to take us all the way through this first half of the thing about heat and actually through a lot of the second part as well. Radiation is a big theme when you're talking about moving heat around, so we want to make sure that we have a good dictionary definition of what we mean by radiation and how radiation is moving energy and so on. Radiation, to use a nice glossary type definition of the word radiation, is the transfer of heat in the form of waves in the electromagnetic field, we'll come back to that, between two objects that are not touching. So let's parse this here. There's this business of that the two objects are not touching, and we're transferring energy between them. Now, the way they're happening, that transfer of heat is happening is by waves in the electromagnetic field. Oh my goodness, let's get that sorted out as to what we mean by that. What is the electromagnetic field? Well, frankly, there's a whole lot of philosophers and physicists who'd like to know that too, but in some sense, we are all surrounded by an electromagnetic field. And it is a field in the same sense that like gravity is a field and so on. There's a field around us, and this electromagnetic field has waves in it. To understand what that means, let's think about being in the ocean. Let's say you went to the beach and you wade out into the ocean a little ways and you looked around closely. You would see that there's a lot of waves passing you. Some of these waves would be like the big kinds of swells that are, fairly tall and you could like surf on them or whatever. Some of them, though, if you looked closely, would be like little ripples. And you could see them going by. And they go at a different speed and maybe in different directions. And they have a different amplitude, how tall they are and so on, than the big waves did. And actually, if you stood there in the beach, in the water for like a day, you'd see over the course of the day that there's these very long wave phenomena that are going by that are the tides, right? Where like, for 6 hours the water was higher, and then for 6 hours the water was lower, and so on. There's in fact a lot of different kinds of waves passing you while you're there on the beach, and the same is true about all of our lives, all around us. We are immersed in the electromagnetic field, and there are waves passing through it. And these waves in the electromagnetic field are radiation. They are ways of moving energy from one object to another. They can be things like light or microwave radiation in your microwave oven, or lots of different kinds of radiation that we're going to be seeing in just a little bit. And they're all just different types of waves. Now, just because your book kind of gets this complicated, and I know a lot of you will have taken the ATS EVS 105 class where it gets a little complicated, maybe you've also heard about photons. Photons are another way of thinking about radiation. Photons can be thought of as like little particles of light, or particles of heat, or something like that, or particles of infrared radiation, or whatever. Sometimes that can be a useful way of thinking about radiation too. Where you're thinking of it not so much as like a wave that came by like when you're on the beach, but if you thought of it as more like a particle of, let's say, water coming past you, okay? If you were on the beach, you could think of particles of water coming past you. And in the same way, photons can be a useful way of thinking of radiation too. So sometimes I'll slip up and say, we're talking about waves of radiation, and sometimes I'll say photons. But they're both similar ideas, and in fact, it's a big part of modern physics to understand that radiation works kind of both ways. It's both a particle and a wave, but whatever. There's lots of different types of radiation out there. You might have heard, for example, of ultraviolet radiation. Ultraviolet radiation is the kind of radiation that comes from the sun and gives you sunburn or skin cancer. It damages crops. It's a dangerous type of radiation. It causes skin damage and so on. But on the other hand, visible light is a type of radiation as well. It is a way of moving energy, in this case from the light bulbs and so on to in that case, your eye. But it's just a way of moving energy or heat. We're going to use the words heat and energy kind of interchangeably. Infrared radiation is another type of radiation, like when you talk about like night vision goggles and things like that. It's a type of radiation that you can't see with your eyes, but it is being given off by objects regardless of whether or not there's any light in the room. Your microwave oven gives off microwave radiation, another type of radiation that moves energy from, in this case, the magnetron of the microwave oven into your food, but it is a way of moving heat in the form of, in this case, microwave radiation. X-rays. When you go to the dentist and she takes X-rays of your teeth, that is a type of radiation where the equipment is is sending radiation through your body, and that radiation passes through your soft tissues but is absorbed by your bones, and so you get a picture of where the bones are. Radio waves, like how you pick up radio stations, or how your cell phone tower communicates with the tower, and so on. That's another type of radiation. All these different radiations are really all these different types of radiation here that we're talking about here are all really just waves in the electromagnetic spectrum, or they are electromagnetic field, or they are photons, if that's another way to think about them. And the only way in which they're different from each other is their wavelength. Ultraviolet radiation is a particularly short type of wavelength. It has a wavelength on the order of microns, or millionths of a meter. Radio waves, on the other hand, are also waves in the electromagnetic spectrum, but their wavelength, the distance from the peak of one wave to the peak of the next wave, is on the order of meters. So they're like 1,000,000 times longer than photons or waves of ultraviolet radiation. And you can see actually on that diagram here that all of these different types of radiation have a slightly different wavelength. Okay, all they are is just different sizes of the waves. That's the only difference between all these different types of radiation, the only way in which they vary. Now, we often get this idea of radiation, in your day-to-day life, if you hear about radiation, it's often in a spooky kind of way, or whatever, that it's dangerous or something like that. But keep in mind, we're just talking about what radiation is a way of moving energy. Everything in our day-to-day lives is emitting radiation. And I don't mean that in a little, yes, everything's giving off radioactivity, and no, radioactivity is something different. Radioactivity is like, what uranium atoms do, and so on, or radon in your basement, and so on, that causes cancer. We're just talking about moving energy here. Okay? Some forms of radiation are harmful for you, but it's important to understand that literally everything in the universe gives off radiation, and kind of a lot. It just depends on what kind of radiation it is, namely what wavelength it is. A light bulb is principally giving off radiation that is in the wavelengths of visible light. You are giving off radiation right now, as it happens. We'll learn the radiation laws in just a little bit, but the radiation that you're giving off is primarily in the form of infrared radiation. But make no mistakes about it. If you could see infrared radiation, we would see that you're giving off about as much infrared radiation right now as a light bulb is giving off light. Okay? You're not giving off a small amount of infrared radiation, you're giving off a lot. Okay? Everything, it's part of what it means to be matter. Everything gives off, or emits, to use the right word, emits radiation. The only difference is how much and what kind or what wavelength of radiation it tends to be. Now, we're going to learn two important radiation laws here. Now, in the textbook, it actually gives you the equations for each of these laws. And I can't remember right now, I have different versions of the homework set that we use different semesters and so on in this course. I don't remember whether the one that you have this particular semester has questions that involve the equations. What I will tell you is, if you have a homework problem that involves the equations, you've got the textbook right there in front of you. Go ahead and use the equation. It's not that big of a deal. Put the numbers in and pound on your calculator. I will tell you, though, that the quizzes themselves don't use the equations. There'll be word problems where you answer questions about what causes it to emit more radiation or less radiation, or shortwave radiation versus longer wave radiation. You won't actually need to know the equations on the quiz. Alright, so the first of these two equations that we need to know is Stefan Boltzmann Law. The Stefan Boltzmann Law, is about how much radiation an object gives off. Here we're talking about per unit of area of the object. Because obviously a smaller object gives off less radiation than a bigger object, just because there's more of the stuff, more matter, to give off radiation. Stefan Boltzmann Law says that the amount of radiation that an object emits is determined by its temperature. The hotter an object is, the more radiation it's going to give off per unit area or whatever. So hotter objects emit more radiation and cooler objects emit less radiation. Okay, I don't really have a hard time picturing that, okay? I can kind of imagine, if I had some very hot object in the room right now, even standing far away from it, I could probably feel the radiation coming from that object and making my hand hot, okay? Whereas a cooler object would be emitting less. That is not a hard rule to picture. The other radiation law that you'll need to understand, again, you don't need to know the equation for the quiz, is Wiens Law. And Wiens Law is about the type of radiation that the object is emitting. Now, any given object is emitting radiation on a number of different wavelengths, but we're asking, where is most of it? Where is the most radiation that this object is giving off? In terms of like what wavelength is it? Is it visible light? Is it infrared radiation? Is it microwave radiation or whatever? And what Wiens' law tells us is that the type of radiation being emitted by an object is also determined by its temperature. Hotter objects emit mostly shortwave radiation, and cooler objects emit mostly longwave radiation. Which makes good sense if you think about it. I mean, that light bulb that's shining on me right now to make the light from recording this video, the filament of that light bulb is really, really hot. That's how a light bulb works, is the electricity flows through that filament and gets it ridiculously hot, like about the temperature of the surface of the sun, and that filament then begins to give off enormous amounts of radiation, and that by Stefan Boltzmann Law. And by Wiens' Law, that radiation is mostly visible light, a very short-wave type of radiation. On the other hand, I'm emitting radiation right now, because I'm made of matter, but my temperature is nowhere near as high as the filament of that light bulb, and as a consequence, I'm mostly emitting, according to Wiens' Law, long-wave radiation, mostly in the form of infrared radiation, also some microwave and some radio waves and things like that. So, really, really super hot things emit lots of radiation, and that radiation has very short wavelengths. Things like visible light, ultraviolet radiation, and so on. Cooler objects, things that are kind of at the temperatures of our day-to-day lives, like the ground, air, clouds, you, me, etc., we emit radiation too, because we're also made of matter, but it's mostly long-wave radiation. Infrared, microwave, radio, stuff like that. So if we're talking about what's going to be determining the temperature of the atmosphere, and we see all this radiation is moving, we had a sensor that can measure all this radiation coming and going and being emitted by different objects, we'd see that from the point of view of the atmosphere, there'd be two kinds of radiation. There'd be this really shortwave radiation, things like visible light and ultraviolet radiation, that's primarily coming from the sun, right? I mean, from the point of view of the atmosphere, there's one big thing that's giving off a lot of shortwave radiation. It's that giant ball of nuclear fire we call the sun. On the other hand, a lot of radiation is also passing through the Earth's atmosphere that is in the form of very long waves of radiation, things like infrared and microwave and so on, that's being emitted by the cooler stuff down below the atmosphere, the ground, also clouds and molecules of air and so on, and that's going to be long wave radiation. In fact, we can kind of, I'm sure I have a slide later that actually shows this, but we can kind of then use these words a little bit interchangeably. Shortwave radiation in the atmosphere will also be called solar radiation because it's going to pretty much all be coming from the sun. That's pretty much the only thing that's hot enough to be giving off things like light and ultraviolet radiation. On the other hand, long-wave radiation is going to primarily come from terrestrial sources like the ground and clouds and air molecules and so on. So we're going to call long-wave radiation terrestrial radiation. You'll see those terms come up lots of times kind of interchangeably. This business of emitting radiation is really interesting. I mean, the object that is actually doing the emitting, like the filaments of the bulb of light or me or whatever, it takes work to do that. Actually, my skin right now is emitting long-wave radiation in the form of infrared radiation, and that's work. It takes work to create waves, just like if you wanted to create waves in the pool or in the ocean. It's work to create those waves. You gotta bounce up and down or whatever, and it's exactly, the molecules in my skin do work to create those waves. And that extracts energy from my skin or whatever, and therefore it cools me. Emitting radiation is a cooling process. Here we have a lovely camping scene on this picture right here, and if you've ever been camping on a nice cool evening or whatever, you know that over the course of the night you get colder and colder and colder, right? Because all night long your tent and the ground around you and so on is emitting long-wave radiation, and that takes heat away all night long. It gets cooler and cooler and cooler. In contrast, the opposite is true. One of the things that can happen to radiation is it can be absorbed. As I sit here underneath this rather bright light that I'm using to film this right here, a lot of the energy that is coming from that light in the form of visible light, photons and so on, is being absorbed by me, and I'm getting really quite hot sitting right here underneath this bright light right here. Absorbing radiation means that when the photons or the waves of radiation encounter an object, one of the things that can happen to them is we can absorb them. And that energy is then put back into these, my body or whatever, and increases my temperature. You can kind of picture this if we go back to our analogy of like the ocean or whatever. You could imagine that you could make a machine that like somehow or other like took energy out of the waves and produced electricity or something like that, okay? You could be taking energy out of the waves and using it to increase temperature or whatever, to heat something up or whatever. So anytime you absorb radiation, your temperature is going to go up. Look at that, what's going on in that little picture here. It's a classic example of a little science experiment. On a sunny day, the ground has been absorbing a lot of shortwave radiation from the sun and has been getting very hot, and they're frying eggs there on the sidewalk there as a little science demonstration to show how hot the pavement is getting. Absorbing radiation is actually only one of the things that can happen to radiation when it hits an object. We're going to actually spend quite a bit of time talking about all the other things that can happen when energy from the sun in the form of radiation hits clouds and air molecules and so on. But first, before we get to that part of the lecture, let's actually let's do a few more quick questions. Question 4. Colder objects emit blank radiation than warmer objects do. Less, more, or shorter wavelength? Which of these is the correct object based on the radiation laws that we've learned? Make a choice from those 3 options and get a little feedback before you move on to question 5.